All right, we'll go ahead and get started. How's everybody today? I hope you're enjoying our weather.
Definitely.
Better than home, right? Better that white stuff that you send me pictures of.
That's for sure.
We have our next speaker, or last speaker for today, is Keith Venables. I hope I pronounced that right.
Yeah, perfect.
Great. He's born in London, and he's an astronomer. He majored in astrophysics. You're currently working in the defense industry.
Yeah.
But you didn't tell me what you were doing over there.
I'm not allowed to tell you.
He's not allowed to tell us. It's national.
He's going to kill you.
But you're an amateur telescope maker, and you're here to present us about dark adaptation and smoking and alcohol. So this is the more important part.
It's all linked. And chocolate brownies.
Chocolate
brownies.
You learned that from us.
Yeah. Okay, thanks for the introduction. I'm a great fan of your US star parties. I've been to the TSP 11 times, and this is my third time here. People think I'm crazy to come across here, but I've already done more observing in 2 nights than I have in the last 6 months in the UK. So that's how bad it is over there. So I'm going to talk about dark adaptation. It's something, actually sort of street lighting and preserving dark skies is something I've been passionately sort of interested in for the last 5 to 10 years. And I helped change government policy where the UK skies are getting darker slowly. It is now illegal to shine a light onto your neighbour's property and to shine a light upwards. So we're making progress. So I'm going to get a bit more useful, and this is of complete relevance to you people at star parties and other things. If we could turn off the main lights on this side and leave that one on, if that's okay. The reason for that is if we got time at the end, there's an experiment for you all. I have some test charts, and we're going to measure your dark adaptation and your recovery time. So that's what I'm going to talk about. A bit about the eye. If you're going to do astronomy, you need to know about light in the eye, how we get dark adapted, importantly, how we lose it, or how not to lose it. And then some experiments that were done in 2007 at the TSP. So the eye is a pretty fantastic thing. It's interesting that the eye has almost evolved the same way in almost every creature on the planet. There are a few variations. But you compare it with the latest digital camera, we've got 100 million pixels in our eye. I think a Hasselblad is getting close to that. 80-degree field of view, 1 arc minute in the center. And look at the sensitivity range, 0.01 lux to 100,000 lux. The dynamic range of the eyes. And we get 2 of them. Well, we certainly start off with 2 of them, those of us who are fortunate enough. We get 2, they come in pairs.
So, but because the 80-degree field, I guess it's pointless to get an ethos-eyepiece.
It's can we turn that one out, or did you want that one on?
Well,
you want to see?
It's entirely up to you.
No, yeah, turn that one. I've got plenty of light. So how does the eye get that fantastic sensitivity range? 10 million to the 1. I'm sure you're all familiar with the basic construct of the eye. The retina at the back, lens, and the pupil at the front. And the optic nerve trailing out to the brain. Okay, there's a 10 times sensitivity control. That's all it's got in the iris. Your iris, it expands and contracts as you go into sunlight and into the dark. All that does is give you a factor of 10 of sensitivity control when you go into a dark room or light room. So that's not much. And it's quite fast. As you walk into a dark room, pow, or shine a light into someone's eyes, you can see that move. There's also times 10 at the other end that the brain and the visual cortex can do another times 10 of sensitivity control of the order of seconds. Quite fast again. So you've got control of that one. But the real control comes in the retina, the biochemistry of the retina, 100,000 times sensitivity control. The problem with it, as we all know, it takes minutes for the retina to change that sensitivity. And this is what I'm going to concentrate on mostly. So the retina, if you were if you're an optician and you could, ophthalmist, stare into someone's eyes, and this is looking in, and that's the retina. In the central region are the cones, and there are about 6 million cones, so that's equivalent to your typical standard sort of digital camera. Sensitive to colored light, so you get red cones, blue cones, green cones, sensitive to each color. And they're all grouped together in the fovea, in the region, the foveal region. And they respond to light brighter than 0.03 candelas per square meter. You don't need to worry about the numbers, but we're probably about 10 times that brightness in here at the moment. So you can see color in here at the moment. You can see color on my shirt, on your own shirts. So we're in the region of using your foveal vision even in this dark room. And certainly when you go out, you're using your foveal vision. And that's called photopic. Around the outside of the retina are your rods. And we've got 100 million of those. That fills you out to 80 degrees. But they're monochromatic. You can't see color with those at all. They get denser out to the edge. There's the gap here where the optic nerve joins onto the retina, and that's your blind spot, which you're not aware of. You've probably done some tricks, some experiments to find your blind spot. You can find it. There's a sweet spot. Talk to Stephen O'Meara. It's not always in the same place. It's usually on the other side of the blind spot, where you have more rods than anywhere else. And something you could try at night is using your averted vision. You know, you look away from the faint fuzzy you're trying to look at. Don't always look in the same direction. Try looking around it, and you'll find that you have a sweeter spot than somewhere else, and the density of rods is better there.
Could it be side to side?
It can be anywhere. It's usually on the opposite side to where the optic nerve leaves, but it's not always there. Okay, and it's the rods that take us into dark adaptation, and that us astronomers love. These are the ones that we want to use. Okay, this is there's some old stuff here. Good old 1960s, I think this work was done. So turn the lights off, and what happens to your vision in time? So in about 7 minutes, your eyes get adapted to quite dim conditions. So if you would come in here from outside now, within about 7 minutes, your eyes have got adapted enough, and they won't go any further, and you can see perfectly in this room as what you want. Okay, so you can get down to, that's a pretty nice response time, and if you were to stay in here, it would flatten out. We all know the period that if you go into starlight, which is about down here, it takes 30 to 40 minutes to get fully dark adapted. People think it takes longer. It's actually, as you can see, the curve is flattening out there. After 30 to 40 minutes, you are fully dark adapted. You may become more aware of your surroundings, okay, and other things, but your retina isn't getting any better. So that's the sort of period of time it takes to get dark adapted. And what of course we don't want is someone to then shine some lights in our eyes, and then you've got to, oh damn, I've got to wait another 30 minutes before I can. So this is the science at the moment. Okay, so how bright can this light be? Well, this 5 here, the light level in here, actually 260 Trollens is about the light level in the toilet blocks here. It certainly was at TSP. So if you go into a nice red lit room, right, come out again, very quickly your eyes become sensitive. Okay? Very, very quickly. Of course, what happens if 1 is 400,000, that's daylight, so if you're equivalent of someone flashing a headlight in your eyes for quite some period of time, it can take 30 to 40 minutes to recover. Okay, so it's not rocket science. The dimmer the light, you can recover from quite quickly. Now, I'm going to use that information later. Okay, so it's not just white light, it's how bright is that light that's going to ruin your night vision. And potentially, if it's not very bright, it doesn't ruin your night vision at all. No one ever lost their night vision by looking at a faint fuzzy through their telescope, but they're looking at white light. Okay, so there is a level of white light that doesn't ruin your night vision. How long the light? How long a light can we stare at, get interrupted by, before it starts causing us problems? And the answer is actually, you don't want to be in this region of 10 minutes of light. It's taking you a long time to recover. You want to be in the sub-minute region, and you recover very quickly. So there's some science here that's saying, actually, if the lights are dim, relatively dim, you only look at them for a minute or so, your dark adaptation is not going to go away. Now what's going on here is the question. So, and I'm talking about the retina because, as I said, this is where all the power of our eyes comes from, this 100,000 sensitivity. So when we're dark adapted, there's the protein in the rods called rhodopsin converts into retinine under dim conditions. Now I've got a little picture of this coming up. That conversion of rhodopsin to retinine produces an electrical signal, and the brain says, aha, I can see light. That is vision. That is seeing light. That conversion of rhodopsin into retinine under illumination produces an electrical signal. We see it. That's what the brain triggers as light. So that chemical reaction, rhodopsin to retinine, is absolutely critical. We don't have an infinite supply of rhodopsin in us, so we have to convert it back. The retinine has to be converted back to rhodopsin so as to go through that chemical process again of seeing light and sending out electrical signals. Okay? That biochemical process of converting retinine back to rhodopsin uses oxygen and glucose. I said I'd mention chocolate brownies. We're getting there. Oxygen and glucose, okay, will get you, are fast enough to get you back to the rhodopsin as long as you haven't had more than a few minutes light. Okay, that chemical process in your retina can cope with stacking up enough quantity of rhodopsin for you. Okay, as long as it's not having to work too hard. If your eyes are working too hard on white light and you're using up the rhodopsin, the retinine can't be converted back. It's going too fast and gets converted back into vitamin A, which is the original source of it. Now you're in trouble. Now it takes 30 minutes to get back. So this is the sort of chemistry that's going on. So during the day, and as it gets dark, your body uses up vitamin A to produce rhodopsin. Okay, and until it's done that, sad guy, he can't see anything. So you need 30 minutes to build up your stock of rhodopsin at the beginning of the night. Once you've done that, that's fine. The photons entering the telescope, entering the eye, hit his retina, convert rhodopsin into retinine, which produces an electron, hits the optic nerve, and we're happy because we can see the faint fuzzies. Oxygen and glucose are used to replenish our supply of rhodopsin. Everything ticks along nicely. You can go through all night, assuming you've got enough oxygen and glucose to maintain your dark vision. But what happens if you get too much light into your system? Okay, you run out of rhodopsin. You have to go back to your vitamin A reserves to produce some more. That takes 30 minutes to get your rhodopsin back again. Do you all see that process?
Quick question, what if you pop a vitamin A pill?
Sorry?
Quick question, what if you pop a vitamin A pill?
That will help, but it still takes 30 minutes. So very few people are deficient in vitamin A. I mean, if you are, then yeah, you will have poor vision. People used to say in England, eat your carrots and you have better night vision. Well, you get vitamin A in carrots, you also get a lot of other things. But yeah, you need to have good vitamin A, but that's not as important as actually the glucose and oxygen. So for us astronomers, we've got to keep the rhodopsin in our retinas. It takes us 30 minutes to get there from the vitamin A. Okay, we need to do this conversion back to retinine. And we need to keep our exposure to bright lights. Well, that's obvious. We all know that one. Note that each retina acts independently. The irises and the cortexes are actually linked. So if you shine a bright light into one eye, they tend to both react. But this process of protecting or using up your rhodopsin and your retinine in your eyes, your retinas, is independent for each eye. So the old trick of putting an eye patch on is absolutely useful. Or if you have to go into the toilet block, you just have to go, close your observing eye. Stumble around with one eye, we can cope. Right? It will save the dark adaptation in that eye completely. Okay. So, keep your oxygen and glucose levels up. Go and eat lots of chocolate brownies or other things. It really is important. Smoking increases that dark adaptation time by 20%. That's not so bad, but it reduces your sensitivity by 50% while you're smoking. Do not smoke and observe. I mean, as a non-smoker, I don't want the smell, but actually you are destroying your night vision because you haven't got your oxygen left. What oxygen you've got left in your bloodstream is being used by your brain and your other parts, and your retina isn't getting any. 50% reduction in sensitivity. Absolutely enormous. Reasonably heavy drinking. I'm told that's of the level of a bottle of wine during the night. So a glass of wine every hour or two is about a 20% hit. And then another 20% at the brain. So that's not good. Plus not sending you sleepy as well. Okay. So that's why I put smoking and drinking in the title. And I should have put chocolate brownies in as well. Or whatever form of sugar you can. Clearly keep lights and dim on, etc. Keep your blood sugar levels up. I'm not taking a cut from Mickey's Kitchen here, by the way. Okay, so let's talk about red lights. So the rods that we have around our periphery that we use for nighttime vision aren't very sensitive to red light. So if you shine red lights in your eyes, the rods don't see it. They don't use up rhodopsin. They don't produce retinine. So you're not using your valuable reserves of rhodopsin that you want to hang on to for your night vision. So that's why we use red lights. Yeah, that's why submarines, they always go to red lights, whatever. You'll see people using green lights a bit soon. Okay, that's for an entirely different reason. Green lights will ruin your night adaptation if you use them at normal levels. But they do have a place. So we have red torches. They must be dim. They must be truly red. Now, there are some people putting cellophane over their torches, and there are some red LEDs in super bright torches that look a bit orange. They don't look dark red. They will destroy your night vision. Okay? You might as well use a white light, and you really annoy everyone else. Okay, so you're looking for really, really red, and you can see it. You can see someone walking across the field, and their torch is a bit orangey. Yeah, dreadful. But the problem we have is that shine a red light on your map, and it's or whatever. You can't see anything. Yeah, you certainly can't see the colours in the map. And if you're using a laptop and you've got a red gel, if you've got a laptop, make sure you've got it. There we go. One of these. Yeah, have one of these. Yeah. You can't see colours anymore, so you turn the brightness up even more. So we get into this vicious spiral. People using red, we turn them up bright. We think that's all right, surely. Nothing wrong with bright red light. But after a while, it does become a problem. So the question is, how bright a red light can be before you lose dark adaptation? Does it matter how bright it is? That's the question. And then white lights. Well, as I said, very dim white light does not affect dark adaptation. You're looking through your telescope, you're looking at very dim white light. You're not losing your dark adaptation there. So there is a level at which white light is okay. And as we showed from those curves, actually recovery from short exposures of strong white light can be very fast, can be of the order of half a minute. Okay. So the second question is, what level of white light illumination has little effect on dark adaptation? And I did some research and found there was almost nothing that could tell me that answer. So I did an experiment at 2007 TSP, got some willing volunteers who happened to be camping near me and didn't have no choice. We looked into this. What we did is we looked at screens, and there's a typical. So I got a laptop, and I told them to look at this in a box, and they had to look at this screen, and I had variable brightnesses of red, variable brightnesses of white, and they looked at the screen for 30 seconds, and then they looked away, and then we measured how long it took them for their dark adaptation to return back to where they were. So these were volunteers who had to be willing to lose their dark adaptation for a couple of hours while I kept making them look at bright lights, whatever. Okay. And there's the white one. How did that happen? Obviously, I wasn't talking faster. So and there's white. Oh, beautifully clear. Okay, but that's a strong bright one. And I had some dim ones as well. And this is the results that we found. Okay, so this is your font size. So if you want to read nice, small 10-point font, okay, you can either have white light at -2 log. I hope probably don't understand these, but there's a factor of 10 brightness difference between there and there. So you can have white light or red light. You can see the same detail at about 10 times fainter white light than you can red light. Alternatively, to see that level of detail using red light, you've got to have your red light 10 times stronger than if you had the white light. So that sort of order. Okay. If you're really big fonts, it really doesn't matter because you can read big letters in red light. You don't have a problem. It's when you're trying to read that small detail on your screen or on your map, okay, and you've got a red light and you're turning the power on the red light up, okay, and we all prefer to use white, wouldn't we? So there's some numbers there and that puts some figures. Starlight is about here. Your typical laptop is about that brightness, and the toilets are way over there. So you have no problem reading in the toilets from that one. Okay, so having made my willing volunteers look at these screens and do their legibility test, how long did it take for them to recover back to their dark adaptation? Okay, so typically, if they're looking at a screen, a laptop screen around about here, which is quite comfortable to read, okay, it takes 30 seconds with red light. You know, turn away from the screen, go back out. 30 seconds later, full dark adaptation has returned to those people. White light was only about 50 seconds. It wasn't 5 times longer, it was just a bit longer. Another 10 to 20 seconds longer.
These are after 30-second exposures to the light, right?
Yes, we worked out that they could, that's enough time to look at your map, do what you want to do. It would be correspondingly shorter if you looked for only 15 seconds, the recovery time. So that's that. And so if you combine those two sets of data together, if you want to read 10-point font on your map or your laptop screen, you have the choice of using red light and having a recovery time of about 40 seconds, or white light and having a recovery time of 50 seconds. Okay. This sounds like I'm telling you to use white light to read your maps. Well, you can. You can, as long as, now I'm not doing a plug for Astro Gizmos here, as long as you put your laptop in something like that. Okay, or a cardboard box, which is fine, but you're not allowed to just point it away from everyone else. You have to close it and open it. All right? Because this is only working for you. This is your exposure to that light, and then you walk away. You don't want to expose anyone else to that white light or that red light. Okay? So what I'm saying is you can read maps and laptop screens using red or white light. You won't damage your night adaptation by using dim white light, but don't let anyone else see that light And the reason is
You get shot.
you get shot. Okay. So that's the summary. We have to keep the observing site dark in general, because your eyes dark adapt to the average. Your eyes have dark adapted in here to the lighting level in this room. They won't go any darker. No matter how long you stay in here, your eyes won't get any better dark adapted than it is in here. If we suddenly turned off all the lights and the sun and it got darker still, you wouldn't be able to see for a long time. You'd have to dark adapt for another 20 minutes. So you only dark adapt to the level right here. Last night, around my observing patch, and if there's anyone close to me, I apologize, I could see 47 green and blue LEDs from my telescope. Okay, and there were 4 laptops facing away from me, illuminating the bushes and their tents. That is bringing the overall brightness up. Yeah. They have to be blocked out. They really do. It's not actually as dark here as it is at TSP. The sky glow is really, really bright, so it almost means. But a bit of black tape on your LEDs will do wonders, especially blue. There's a lot of blue LEDs on laptops and things. Kill those with black tape. They are completely ruining, even if you're 10 feet away from them, they're ruining someone's night vision. Please, please, please do slug them. They've got to be shielded. So you shouldn't get shot as long as you have your nice white reading map or your thing inside a completely sealed box that no one else can see. Right, we're going to try an experiment. See whether this works. If you want to, there's bits of paper there. They're test charts. I don't know whether you can see them. No, do not. Don't turn the lights on. I haven't quite got enough for everybody. You might have to share in groups there, could you? They look like black bits of paper on one side. If you can share near someone. There we go. You can share. Okay. Oh, I've got a few left over there. Yep. Have another one. Yeah, you've got lights near you. That's not going to work. Okay. Right. If your eyes are really dark adapted, I don't know whether... So what we're going to do is it's a test chart. Okay, across the middle from left to right are numbers getting dimmer and dimmer. And just to make sure you're not cheating, after a while they stop becoming numbers, they become letters. Okay, so in theory you're now dark adapted. Okay. Oh, close the door. Okay, we're going to do something similar. We're going to stare at a bright screen for a period. Okay, and then we're going to measure how long it takes you to get back to your level of dark adaptation. And then we're going to repeat that. So I'm glad you're going to try and get it to go darker in here. To the point where, okay, now that's the test chart. Okay, that's just so you can see now. Okay, if you look at the color bar at the top, you shouldn't be able to see color. Can anyone see color? Yes? Then you are too much light near you, yes.
You mean on the screen?
No, sorry, not on the screen. So on your piece of paper, on your piece of paper, the band across the top, you should be able to see a grey bar with some variations in it. You shouldn't be able to see color. All right, that's proving that in this room now, we've just gone in to scotopic vision. Okay, we're using rods only. Your cones have stopped working. Yeah. Okay. Now, certainly on mine, I can see A. I can get A. Can everyone get sort of halfway or 2/3 way across the bar?
Halfway, but I can't see what they are.
Oh, well, no, you're not required to know. Yeah, you don't, sorry, can I, yeah. You don't have to know it's an 8 or